going on. It's all being done with addition, which is kind of amazing if you think about it. Now, what's controlling this machine
with locker room
is this set of cams over here. And cams are the kind of thing that they follow along on some sort of an arm. There's a little gear, a little wheel.
I don't see where the numbers are, where the results are.
And the cams are misshapen shapes. They cause the arm to get pushed.
Right down there goes 0
But he didn't believe in springs.
219.
He did not believe in using springs to bring something back. You could push it out, but to bring it back in, you would not pull it back in with a spring. Instead, he would have a counter arm that was designed to push it back the same way you pushed it out. Okay? So every single one of these is a pair of arms.
So it's the ones on the
One on one camshaft and one on another camshaft. And so it pushes one out, and then it pushes it back. And it pushes one out, and it just does that dance. So let's go through another cycle. Now, some of you said you like being in the back. It doesn't matter to me where you stand. You understand now that this is all being done mechanically. Okay, that's the beauty of this thing. And this was a design that he had done starting in 1821, and by 1837 he had pretty much gotten it drawn out. And the guy who was working with him, building this, actually working on making the parts, a guy named Clement, wasn't getting paid. And he got into a little bit of a rift with Babbage, and he quit. He basically said, I'm not going to do this anymore. And British law said that whoever made the parts owned the parts. So although he had already made him a little 3-column model that he could use to demonstrate, the big 7-column machine that he was trying to do never got built. The government was actually funding this project, but it had taken him so long, they basically were withdrawing their funding. They were saying, we've spent 17,000 pounds of British money. And by the way, a pound, a typical salary back in those days was 50 pounds for a year. Okay, for an individual. 17,000 pounds is going to take care of 350, over 350 people.
And they've been working on it for 15 years.
Right.
15 years.
So the British government basically gave up. And when Clement had this little tip and quit, British law said that the guy who kept the parts. So he kept all the parts. And Babbage got nothing except the little, what he called the beautiful fragment, the little piece of the machine that was supposed to be what a demonstration model. So at that point, he turned his attention to some other project that happened to be the analytical engine. And you can see some pictures of it on the wall. He went to the government with that, said this is going to be a real computer. It's really going to be able to compute add, subtract, multiply, divide, do logic, everything else. They said way too expensive. Not going to do that either. So he gave up. But in the process of doing that design, he discovered how he could take this 25,000 part machine that was going to weigh as much as a locomotive and reduce it down to 8,000 parts and only weigh 5 tons. So he spent his next 2 years, 1847, 48, 49, designing the difference engine number 2, okay? In its entirety, not just, because he hadn't even finished number 1. But now he was able to do the entire difference engine number 2, including the printer. And the government wouldn't buy that either. So he put it all in storage. He gave up, went on and did other things. For example, he invented the cow catcher for the locomotives. There's all kinds of, he was an inventor. At the age of 80, he died. Everything he had was given to his son, and his son eventually gave it to the London Science Museum, and they put it in their vault. And there it sat for year after year after year, nobody knowing anything about it. In 1985, Doran Swade became the curator of the London Science Museum, and he went down into the vaults to see what they had and discovered these plans of the Babbage difference engine number 2.
Rank it up to 10.
Let's go all the way to 10.
See if you get the right answer. What am I on? 7.
You're at 8.
I'm on 8. We'll go 2 cycles, and then we'll see if we get the right
And watch the back if you like. So there we're at 9. Transferring 9 to the printer. Restoring the 9. Now we're going to 10. Transferring 10 to the printer. Coming back.
And pretty soon we'll give you 5 cycles in a row.
Okay. So the answer we have on here, if someone would like to take a look at x equals 10 while I read it off, I have all zeros in a 2, 2, 9, 5, 1, 7, 8, 1. Amazing. You never get the wrong answer with this machine. How does it do it? What do you set up the machine to do? Do you put the coefficients of the polynomial into the machine? No. Because that won't come up with an answer properly at all. You have to put in something called the method of differences table. Let's take a look at the table. Believe me, you'll understand this. I've got two very simple polynomials here. X squared plus 1 and x cubed minus 2x squared plus 1. And I'm going to work with this one that's the third order polynomial because it's probably the better example. Depending upon the order of the polynomial, you need to have as many difference columns as that order. So for a square, you need to have 2 differences. For a cubic, you need to have 3. And for a 7th order, you need to have 7. And of course, you always need to have the result. So you add 1 column more than the exponent. In this case of the third order, we've got 4 columns. In the case of the square, we've got 3. You have to compute that number of columns worth of answers by hand. So in the case of this one, I have to compute 4 sets of answers by actually figuring out for x equals 0 and 1 and 2 and 3 what the answers are. So if we put in x equals 1, 1 cubed is 1, minus 2 times 1 is negative 1, plus a 1 is a 0, and so the first result is 0. And for the x equals 2, we get 1. For x equals 3, we get 10. For x equals 4, we get 33. We get these first 4 sets of answers. We need 4 because we need to have 4 columns. Now, take consecutive answers and subtract them one from the other, and write the answer on the line of the number you subtracted. So if I subtract 0 from 1, I get a 1. 1 from 10 is 9. 10 from 33 is 23. So I get 1, 9, and 23. Remember, this table doesn't go any farther than 33. 1 from 9 is 8. 9 from 23 is 14. We get these two. And 14 minus 8 is 6. We now have 6, 8, 14, 1, 9, 23, 0, 1, 10, 33. Just this diagonal right here, like this. All right? Now, how does the machine work? Remember I said it does the odds to the evens, and then it does the evens to the odds? It does it with staggered steps. So I'm going to start with this staggered step. I'm going to start with the 8 and the 6 and the 1 and the 9. Now, how much is 8 plus 6?
14.
Okay, and 1 plus 9?
10.
And we write those numbers in the leftmost column. So we write them right below the 8 and the 1. We have the 10 and the 14. Now, having just computed the 14, guess what? We can now do the even the odds. So we're going to do 14 added to 9. Okay, and we'll bring down the 6. And we get now 10 and 23 and 14 and 6. We started with 1 and 9 and 8 and 6. This is now a new staggered step. Ready to do it all over again. So we'll go back and start with that all over again. 6 and 14 is 20, and 10 and 23 is 33. So we get 33 and 20. And then 20 and 23 is 43. Then bring down the 6, and we have the next staggered step. And that's all there is to it. It's all done with addition. Isn't that amazing? Now that's one way to do it.
That's how they calculated polynomials by hand before there was computing machinery as well.
Right.
By hand.
That's how those women whose job title was computer were doing these things. That's how they did it. Okay. They were given the difference table, and they were given the task of being able to do all. But you can do it another way, by the way. I could just take one line, and if I go strictly left to right, 0 plus 1 is 1, 1 plus 8 is 9, 8 plus 6 is 14, bring down the 6. I now have the new line.